All right, let's work on this, and I am going to, it's too high tech for me. All right, so we're going to maximize area. We've got a farmer and we need to make a pasture, and we have a certain amount of fencing, but we do not need fencing along this river. Okay, so let's figure out, let's see, we have 1,600 feet of fencing. Okay, now for the fencing, we're going to need both of these sides, which we've labeled X, and then we also need this width. So plus width, and that is going to take up all of our fencing. So an expression for width would be 1,600 minus 2x. So if I was trying to figure out the area of this plot, I would do length times width. Okay, so my length is x. So I have x times width, which is 1,600 minus 2x. And so I would get 1,600x minus 2x squared. And I'm just going to go ahead and put this in descending order. There's my function. Now I'm being asked to maximize area. This is a quadratic. That is asking me to find the vertex. Okay, so vertex is given by negative b over 2a. All right, and in this, writing it in descending order helps us see that the coefficient of x squared, that's our a, so negative 2, and the coefficient of x is our b, so that's 1,600. So we get the opposite of b, so negative 1,600 over 2 times negative 2, which gives us an x value of 400. Now the y, we get that by plugging our 400 right into our function and figuring out the output. So we'd get negative 2 times 400 squared plus 1,600 times 400. And that gives us, let's see, 320 square feet. What are the dimensions of the field that will maximize area? Okay, so the dimensions are, let's see, we found it, it's 400. So it's 400 by the width, which was 1,600 minus 2 times x, so minus 2 times 400, so that would be 800. So it's 400 feet by 800 feet. All right, and so if we wanted to see how to do this on the graphing calculator, once we figure out our function, then we can type this in, negative 2x squared plus 1,600 x. Okay, if we're being asked to graph it, you know, this doesn't really, it's really hard to see what's going on. Sometimes if you've been doing a bunch of these, your window gets quite, you know, affected by the previous problem you just did. So if you want to go in and just do a normal window from negative 10 to 10 on both x and y, that is zoom. You go to zoom and 6. That's your standard window. Okay, but that didn't even help. All right, so then here, if you're being asked to show, you know, some graph to verify your work, then we would use the fact that our vertex was at 400. Okay, so I usually double that because that's kind of the peak, but I want to see the whole entire graph. So let's go up to, let's say, like 900, and we can count by hundreds. And then we know we're going all the way up to 320,000, but let's go a little bit above that. So maybe 350, oh, I think I have an extra 0. All right, and then that's counting by a lot. So let's just count by maybe thousands or even by 10,000s. Okay, and then we can graph Perfect. All right, and then if we wanted to show that maximum value on our graphing calculator, we can do that, but guess left bound and right bound, and then we go over to our guess and hit enter again. And then that shows us that value as well. Okay, and then you can just take a screenshot of that, and you've got the another way of showing your work on here as well. All right, let's do one more. Okay, so on this one, we've got a man trying to get to point B from A to B in the shortest amount of time possible. But first he has to row across the river, and then he has to walk from where he lands to point B. Okay, so he can walk at 5 miles per hour, and he can row at a speed of 2 miles per hour. So we want to minimize the amount of time it takes him. We want to get him across the river as fast as possible. Okay, so let's see. I'm going to kind of draw this up here a little bit. So if he's got 2 trips to do. He needs to get from A to point P, and then he needs to get to point B as well. Okay, we're letting X be our distance from point P to B. All right, and the distance across the river, this is 1. And it's 9 miles downstream, so this entire length is 9. So then this right here would be 9 minus X. And so I have a right triangle in here, so I can figure out this distance right in here from A to P. We can use the Pythagorean theorem because we have, that's a hypotenuse, so we have AP squared would be the square of each of those shorter legs. Okay, so then AP would be 1 plus, let's see, we have to multiply 9 minus X times itself. So we'd get 81 minus 9X minus another 9X, so minus 18X plus X squared. And then we can take the square root of all that. I'm just going to write this in descending order. X squared minus 8X plus 82. So that's this distance right here. X squared minus 18X plus 82. Okay, so he's going to go that length at a rate of, let's see, that's the slower one, right? He's rowing at 2 miles per hour. And then he's going to go this distance X at a little bit faster rate. Okay, so let's figure this out. We want to minimize time, so we want to have an expression for time. Oops, total time. So I'm going to do the, let's see, distance equals rate times time. So if I divide both of these by rate, I can come up with a time from A to P and then another time from P to B. A to P and then plus the time from P to B. Okay, so time is given in, let's see, that cleared out. So our expression for time is that it is distance divided by rate. Okay, so our total time, T, is going to be the time going from A to P, which we need to do our distance. We just came up with that, X squared minus 18X plus 82 divided by the rate. The rate for rowing is 2 miles per hour. Okay, and then we do our time from P to B. That would be the distance, which is X, divided by the rate, which is 5. Okay, and so our time expression is in terms of X. Now we want to minimize that. Okay, so what we need to do is pull out our graphing capability here, and we go to our y equals, clear out what we had. Just scoot this over a little bit so we can see the whole thing. Okay, so I'm going to do the square root of x squared minus 18x plus 82. But that's supposed to be divided by 2. Gotta go add my other parentheses. Insert parenthesis. Okay, good. So that's the first distance divided by rate. And then we need to do the next one. Plus x divided by 5. All right, now if I just went to graph it, our window is all messed up from before. So let's just go zoom standard, so zoom 6, and just sort of see what we've got. So it looks like there is a little minimum here. I'm going to fix my window. I don't think I need to go so far back for my x, but let's go a little bit further, maybe to 30, and count by 5s. Okay, and then I can see where that minimum is. I'm going to calculate the minimum. So that's number 3, and then we have to do that whole rigmarole of left, enter, and then scoot over to the right, enter, and then guess. And looks like about here, enter. There we have it. Okay, so the minimum x equals 8.56. Okay, so what does that actually mean? Determine where he should land. Okay, so he should land 8.56 miles from point B. All right, and then I can show evidence of my work where I can show this graph. X is in miles and T of X is in hours. And then I'm just going to show what my window is on my graph. Okay, so I went up for Y, I went up to 10, and for X, I went to 30. And I was counting by ones for Y, so 1, 2, 3, 4. It's between 4 and 5. So it looks like it's kind of going here, and I was counting by 10s. Or I was counting by 5s, actually. Make that a little bit better. Okay, and our maximum, it was at about 9, so it was about here. And then I just want to label that point. And it was at 2.26.